Welcome, everyone. Today, we are lucky to have Dr. Belén García back with us again for another seminar.
Are we lucky?
Yes, we are lucky.
Yes, you're lucky. You are.
So Anna was born in Mexico and she had completed most of her studies there. Thereafter, she joined the University of Coimbra in Portugal, where she completed her PhD, and she was supervised by Prof. George Ricardo. Soon after that, she joined UWC, where she was hosted for her postdoctoral fellowship by Professor David Holgate. And now she has joined Chapman University, where she is now on another research project. She's also involved in teaching, and she's shared some of the things she's been doing with research projects recently with the students in her course. But today, we're looking forward to her talk, where she's going to be telling us more about the work she's been doing in concrete. Thank you, Anna.
Thank you. Okay, thank you. Thanks for having me talk again at the seminar. Yeah, so the idea of this talk is to introduce the notion of Coz-inclusions. So, there we go. Coz-inclusions. Right. So for that, I'm going to just go through a little bit of background, introduce some notions, and hopefully we'll get and talk about this new notion. Just to say, this is joint work with Tega and Juan, also both in Chapman. Okay, yes, so context, right? So I'm going to work with a category of locales, which I denote by loc, right? The objects are, our objects or study are locales, and the maps between them are localic maps, right? I think last seminar I explained a little bit more this category, and I also talked about the category of frames, where the objects are frames, which are exactly the same as locales. Let me just remind you what it is. This is a complete lattice where this distributivity law holds, right? So binary means distribute over arbitrary joints, or binary infima distributes over arbitrary supremum, right? So we have this is the join of all the means, right? So this is a proof. Anyways, I won't give more context. If anyone needs some definitions, please just stop me in the middle of the talk. So we have frames and we have frame homomorphisms as the maps between the frames, right? So if we have two frames, so we have these two categories, right? This one is just frames up, right? So it's the same objects and just the arrows are in the opposite direction. So if we have two frames here, we have the frame homomorphism between them. For every frame homomorphism here, we would have a localic map F. And we can identify it with its right adjoint, right? So we have an adjunction. Okay. Yeah, so that's it. That's everything I'm going to say about these two categories. And well, let's always compare it for those who are not that familiar with frames and locales. This is point-free topology. This is classical topology. So top, our objects are topological spaces, right? And the maps are continuous functions. Okay, so this is known to everyone. We have two functors, one coming here, one coming there. Let me just talk about the one that goes from topological spaces to frame to locales, which I denote by omega, right? So given a space, a topological space X with its topology, right? What we do is we take the topology, right? We take the open sets and we get, so we denote it omega X. So the open sets form a frame, right? Ordered by the function. And if we have a continuous map between X and Y, right? Then we send it to the preimage. So everything just swipes, right? Now the map goes in the opposite direction, from Y to X. But the preimage is a frame homomorphism. And of course, we would have the locality map this way, but it's a bit harder to describe. So let's just think of a preimage here. So if you're not familiar with frames, then you can keep thinking about spaces and preimages. Okay? Okay, now, just to remind everyone here, yes, in topological spaces, we have subspaces, right? We can work with all the subspaces, and a subspace in a topological space is just a subset, right? And we give the subspace topology. The set of all subspaces is a power set because every subset is a subspace. So this is all the subspaces. Now this is where things change a little bit here, because on this side, instead of subspaces, we have sublocales, which are sometimes called generalized subspaces. And the sublocales are just subsets of putting L. Right. So I'm assuming L is a locale. This is just a subset that has to be closed under arbitrary means, and it has to satisfy a property with the Heyting operation. I won't, doesn't matter. Okay, what's important though is that if I take the set of all sublocales, this would be all sublocales, ordered by inclusion, right? So for instance, in subspaces, we have the power set. This is actually a Boolean algebra. Right? Complete, actually. It means that we have all intersections, all unions, we have complements, we have everything. But in sublocales, when we take all sublocales, we don't get a complete Boolean algebra, we get something weaker. So we get what's called a co-frame. Right? So we don't have complements, right? Not always. And I want to mention, so this is one of the differences, but for certain cases, subspaces and sublocales usually work the same. Okay? So subspaces, we have open, closed subspaces. In sublocales, we have them too. So we have open subspaces, open sublocales, right? So for every A in L, one can define open A, which is just a set given like this. You don't have to worry about the definition. And we have closed sublocales. So for every A in L, we define the closed one, which is just the opposite, right? And one can check these are sublocales. These two are complements of each other. So open and closed point free work the same as in topological spaces. Okay, now there's other kind of sublocales that I want to talk about. So let's first start reminding you of this special set in a topological context. So let's go back to top. And so we have a topological space, and we have, we say Z, a subset of X, is a zero set, right? Zero set. If there is Y from X to the reals continuous, such that Z is a preimage of the zero, right? That's why it's called zero set. Because this is continuous, of course, every Z is closed. It's a closed set, right? Because it's the preimage of a closed set. And we have its complement, so C, a subset of X, is a zero set if there is a continuous phi from X to the reals, continuous, such that C is equal to, instead of the zero, it's the complement, right? The reals minus zero, or if you may, you could write it like this. Right? This is a co-zero set. Of course, this is open because it's the pre-image of an open set. Continuous. Right? Now, how can we define this in frames? Okay, so let's go back to frames or locales. So let's say we have L is a locale, right? Now remember that I told you that if you have a space X, a frame is, you can take its open sets, right? So when you think of a frame, you're thinking of open sets, basically. So we cannot define zero sets just like that because we're only working with opens. I don't know if that makes much sense, but so the way to define is we first define co-zero things, and then we work out how to define the zero. So, yes. So an element A, an element A in L is co-zero if A is of the form F join F from real to L, right? Where F is a frame so if you see more or less the same definition here, except the order, the direction changed because remember our functor changes every, right? So this is the definition of a co-zero element. Now, we cannot, yes, and I write cos L for all the co-zero elements, right? Of L. Now we cannot define, so as elements, since we're working with opens, we cannot define really zero sets or zero elements, but if we go to sublocales, we can define zero sublocales and co-zero sublocales, right? So a co-zero sublocale is just the open OA, right? Where A is a co-zero element. Right, so I'm just taking the open sublocale given by this element. And a zero sublocale is if I take the close, where A is a co-zero element. Okay, so yeah. So let me then show you how do we have this in general, like a picture of what's. So before I move on, if we have L, so let's say this is our frame L, right? And then let's do here this one. Let's have this as L. So these are all the sublocales of L, right? So we've said we have the open ones, so it would be like our open sets. So let this be open sublocales. Right? Usually we write it like this, OL. And we have the closed ones, which are CF. Closed. One would have to prove it, but it's not hard to see that L and the opens, these are isomorphic frames, right? And L is also co-isomorphic, let's say like this, with CL, because CL is not a frame, it's a co-frame. So let's put it like this. And this makes sense, because if you're in a topological space, the closed behave like the opens, just that you have the other word, right? And so here we have, so I defined co-zero elements here. So this was cos L, the co-zero elements. Here in the open ones, you have the co-zero sublocales. This would be co-zero sublocales L, right? And okay, which I would have another color.
You can use other
This way. Yeah, there we go. So this is, oh, this color is terrible. This one is the co-zeros. Okay, and then we also have the zeros here. Right, these are the zero sublocales of L, right? Again, one can check that this is isomorphic to this. This is not a frame, it's a sigma frame, but anyways, the structure is preserved, and here we have the same but top, right? So more or less this is the picture. What I want to stress here is that if you're working with a frame, you have the elements and you have the zero elements. When you're working with sublocales, then you can actually work with open and closed things. And that's why we can have co-zero sublocales and zero sublocales, which behave exactly like co-zero and zero space. Okay, now let us get now with this context. Okay, let us start motivating the definition of coz-inclusion. For that, I have to remind you of something else. So let's go back to top, right? So you have a space X, right? And let's say you have S, a subspace, any subspace, right? So how do you define the open of S? So an open of S is just S intersection U, for U, an opening L. These are precisely the opens of S, right? And if you have a closed, the same happens with the closed. If this is closed in L, closed of S, right? So the closed and the open sets of the subspace are just the intersections of the space with the open and the closed of the big space, right? This doesn't happen always with zero space, right? And this is what I want to say. So if you have space and you have S here, this is X, you have a zero set, say Z. You don't always have that this one comes from a zero set of the big group. So you don't always have that this, say Z prime, you don't always have that Z is equal to Z prime intersection S, or a Z prime 0 of L. Okay? This is, that they don't behave as nicely as just open and closed subspaces. So that's why people started looking at what's called z-embedding. So S is z-embedded in L if for every zero set Z of S, there is a zero set z prime of L such that z is equal to z prime, right? So what you're saying is that if S is z-embedded, then all the zero sets behave nicely, and they come from zero sets of the big space, right? Oh, sorry, X. Yes. But okay, that goes perfectly well, because then how would you define these for locales? So if you're in locales and you have L, a locale, and S, a sublocale of L, then we say that S is z-embedded if for every zero sublocale Z of S, there is a zero sublocale Z prime of L such that Z is equal to Z prime join S. And also here it's not X, it's S, because it's the intersection S with S, right? So you have a bigger one from big space that intersects here. So in locales we have the same, and it's exactly the same definition. They're equivalent definitions, but more algebraic ones, but I won't go through them. Yes. So now the question is, so you have this, right? So you're in a, let's say you're in a sublocale, and that it's z-embedded, and you have, for every zero set, you have a zero set of the big one, such that if you intersect it with S, you get what you want. Can you have a smallest one? Is there a smallest Z prime that makes this work? Is there a smallest? Right? And one could say, well, yes, why don't you take the intersection of all the Z primes such that Z prime intersection with S is equal to Z, right? And that is correct, but this is not a zero set anymore. This is not zero. This is not zero, right? And so the thing, what will happen is that you will have a smallest one if and only if this is zero, if and only if the closure of Z in L is a zero set. Right? So let me write this. So we say, so this gives the definition. So definition, if L is a locale, S is a sublocale of L, S is coz-included if the closure of Z is a zero sublocale of L for every zero sublocale Z of S, right? So yeah, what I'm saying is every zero sublocale Z of S, when I take the closure in the big locale, I get a zero sublocale of L, right? And then this means that if I have Z, a zero sublocale there of S, and the closure is a zero sublocale, then this will happen, right? so the closure of the set with S will give me the original. This means that coz-included implies z-embedded. Yeah, there is an equivalent definition that I would like to mention here. One can prove it if one is familiar with sublocales and everything. That this definition is actually equivalent, or equivalently, we can say that this means that the cozeros of S, the cozero elements of S, are contained in the cozero elements. Right? So actually John came across this definition from this side instead of the topological side, but okay, so let me give you an example of why this implication is not whole. Okay, and it's quite a nice example. So, example. Okay, so take a frame. Take the frame of reals, right? So I write it like this. There's a special way to construct it. That is why I'm not just writing the open sets of the reals, but these are isomorphic, right? So take the reals. And so yeah, this frame, the reals are perfectly normal. What does this mean? This means that the frame, all the elements of the frame are cozero elements. In other words, every closed sublocale is 0, every open sublocale is cozero. Right? This is perfectly normal. This is Lindelof, etc. It has a lot of properties, right? So now we're going to let us take its Stone-Čech compactification. So I will go through the construction in frames of the Stone-Čech compactification. But let's see, we just have the only thing you need to know is that you have the reals and they embed into its Stone-Čech. This is in locales. They embed in the Stone-Čech just as it happens in spaces. And this is a compact, regular, compact Hausdorff space, compact regular frame. Yes, this is embedded densely here, right? And in fact, we could think of the frame of reals as a sublocale, because this is an embedding, it's a sublocale of its Stone-Čech, right? So, yes. Okay, there we go. So, first thing to note is that the reals are z-embedded. This is a known fact, z-embedded in its Stone-Čech compactification. In fact, they're C-star embedded, but I'm not talking about those embeddings. Right, so what I want to show you is that it's not coz-included, okay? So, yes, one can show, and I won't do all the computations because it gets very technical. One can show that there is an element V in the reals such that V is not in the cozero elements of the Stone-Čech. Right? So this shows that the reals are not contained in the cozero elements of the bigger, which is the Stone-Čech. Right? But remember that the reals is the same as the co-zeros of the reals, right? Because it's perfectly normal. So we've shown that the co-zeros of the sublocale are not contained in the co-zeros of the whole local. So this means that the reals are not coz-included. Right? And in fact, this is also nice because this shows that this thing over here, this also shows that the Stone-Czech compactification of the reals is not perfectly normal. Okay, so let's see. Yeah. Okay. So this shows, well, that so this example is the example that shows that we have that coz-included implies z-embedded, but this implication is not true, right? And what I'm going to do now is I'm going to tell you when does this hold, right? When does this hold? Okay, so for that, let's go back to, well, to spaces, or you can already start thinking in locales. So, yeah, if we have a space or a locale, and let's say you have S, a sublocale, z-embedded tells us that every zero, as I told you, is the intersection with a bigger zero, C prime of the space, of the bigger space. But this is not always the case. So it seems that there are two types of zero sets, the ones that behave nicely, that come from the bigger space, and the ones that don't, right? So for that, let us name the good ones, right? So we say a zero set Z of S is bueno if Z is equal to the intersection for Z prime a zero of F, right? And yeah, so we denote ZS S, right? These are the zero sets of the sublocale S, and we write BCS, a bueno zero sets of S, right? So this is always here. This always happens. The other inclusion, not necessarily, but what we've said so far is z-embedded is telling me that every zero set should behave good. It's of this kind. So this inclusion holds when S is z-embedded. Right? And okay. And we can have, this is for zero sets, we can have the same, we can consider the co-zero sublocales or co-zero sets, but we can also take the elements, right? So we would have a co-zero elements S, and we would have, I didn't define them, but you can guess how to define them more or less. We also have the bueno co-zeros. And of course, every bueno zero set is the closed sublocale of a bueno co-zero element. And of course, this also always holds. This is the same, basically, if you want to think in sublocales or if you want to think in elements. And this just happens when S is z-embedded. Okay? So what do we have? We have that B cos of S is always contained in the co-zero elements of S, right? And we have that, this means it is z-embedded, okay? And we have that if this is contained in co-zero of L, this is coz-included. Okay? So we will define a different kind. What if we think of this being contained in this one without going through the co-zeros of S, right? And that's how we define what we call S is casi coz-included. If the good co-zeros, bueno co-zeros, are contained in cos L. So this is contained here without going through S. So it's like being coz-included, but forgetting about this one and just thinking of this. Because this is also, for those who know, this is also a sigma frame that generates. So it's like looking at the ones that really matter in a way. Looking at the ones that behave good. So this is equivalent. Now let's write it in sublocales. This is equivalent to saying that for every 0 sublocale Z of L, the intersection of S. So this means this is a good, a bueno 0 sublocale of S. If I take the closure, this is a 0 sublocale of L, right? We know that this one, without the closure, this one is a 0 sublocale of S. Now what we're asking is that if we take the closure of this one, we get a 0 sublocale of L. And one can show precisely that S is coz-included if and only if it is z-embedded and casi coz-included. Okay, so coz-included is equivalent to these two conditions together, right? So now let us see that we're not saying that we're not defining stuff that we already have. In fact, one can easily see that coz-included is stronger. Well, we've shown it's stronger than z-embedded, right? And we've shown, well, it's not hard to see for the way of it, how it's defined, or even if you look at this inclusions, it's obvious why this is stronger than casi coz-included. We've shown that this is not true, right? And yeah, so this one's also not true. Wait. No, I wanted to do something else. Yeah, okay, so we have this. Let's see. Yeah. I want to show if these two are related to each other, which they are not, but I will tell you why. So one of the examples already works that the one example that I gave already works. So this one, right? So one. This is not true. Again, if you take the reals inside the stone check, their stone check, we said that these ones were z-embedded, and we say they're not coz-included. because we have this result, we know that they cannot be casi positive. Okay? So this one shows that this is not true. Now, to show that this one is not true, right? I won't have enough time to go through the example, but let me tell you which is the example that works. I mean, there are a lot of examples. One that's easy. I'll just tell you which one it is, and then maybe you do the one. So take E, a space with a discrete topology, not countable. Yeah, uncountable. Yeah. What do I?
Cancel.
E uncountable set with a discrete topology, right? Which means that all the open sets of E is just the power set, right? And then you take X, it's 1-point compactification. Right? So the sets here are, you take the power set of E, right? So the ones that you had for the original space. So sorry, X is just E, and you put a different point, an infinity point, let's say. So you have all the original open sets plus all the A union with infinity, such that A is contained in E and is cofinite. Right? So this ring is the one will serve as an example. We have to give the sublocale. So the sublocale that works, and this is the last thing I will say, if you take S, you take all the B's that are contained in E, such that B is not finite, and you take the B's together with the infinity point, such that B is contained in E and is cofinite, right? So S is the sublocale of omega x. So S is the sublocale of omega x. You will see that S is actually isomorphic to the original space, to the original frame. It's actually the Booleanization, but that doesn't matter. You can show that S is casi coz-included, and maybe I won't have time to do this anymore. And you can show that S is not z-embedded. So this example shows that casi coz-included does not imply z-embedded. So both notions are not related. Yeah. So thank you. Thanks.
What? Let's see. Please go back to that definition. So, in a perfectly normal frame, you have L equals to cos L. What's going to be the relationship between your casi included things and your coz-included things?
I think it would depend a lot on the. So you have these results. Maybe this helps. L is perfectly normal if and only if every sublocale is coz-included. Or you can actually weaken it and put casi. And you can, instead of every, you can say every closed. It still works. So it's like this theorem that every norm, a space is normal if and only if every closed is z-embedded. You have it for perfectly normal. So that's a result. I didn't mention it because yeah. Yeah. So that's I think that's all the question. Yeah. Yes.
Real life naked.
What's nice though is that using this we characterize some spaces.
So because I've seen that it's applied to this key, very important, very few real life. Maybe I think if you guys can think that aspect, I can bring many, because people are afraid of you can bring many examples.
You wrote that two talk, sorry,
Yes,
during the
giving
last
them
talk.
just several of these.
Yes. Logical last and so that dealt a lot. Physical applications.
Yeah, I don't yeah.
In the absence of questions and comments, let's thank Anna once again.